Hi, so today we're going to be talking about the system integration peer review from Team 4. So here you can see is our general Excel data. Here's all of our test runs, and then below those we use some Excel formulas to find some important numbers to describe our data. And then over here on the right of the screen you can see that we converted that data into histograms in order to see about where our average data fell, where most of it fell, where some outliers were, and things like that. So the first thing we're going to look at is the distance issue. So the target and the launcher are about 3.25 meters apart, but because the target is elevated, we are going to account for 3.86 distance. That's about our goal in order for the launcher to shoot the ping pong ball and actually make the target. So as I just said, our goal is 3.86 meters, and today we're going to be working in inches, so that's 151.97 inches. And there's actually a 0.1 meter tolerance, so that's to say that the ball can go 0.1 meters either way from the target, or from our center goal, so the 3.86 meters, and it would still make the target. And so once you take into account the actual size of the ping pong ball, so the distance it would take for the ball to clear the target, not just for the center to hit the side of it, you would get a range of 148 inches to 155.9 inches. So as shown in the Excel, our mean is 150 inches, which is good. That falls within our range. And so down here, we're going to calculate the z-score of the range we just found based off the data we have. So first, we're going to look at the minimum distance required. So that would be that 148 inches. And we're going to, in order to find the z-score, we're going to take that number, subtract the mean, and divide it by our standard deviation. And so that's how we get that negative 1958, which is a good number. It's nice and small. And then we're going to do the maximum distance the same way. So we're going to look at the maximum distance, 155.9, subtract the mean from it, and divide it by the standard deviation. And then that's how we get the z-score of 0.5680. And so now what we can do is we can take those z-scores, which are standardized numbers, and put them into a z-score to percentage calculator. And so we're going to use that negative 0.1958 as our lower bound and the 0.5680 as the upper z-score bound. And then that's going to give us a percentage of 70.74%. So what that's saying is that 70.74% of our data approximately would make the target based off of this range. And then that's also a predictor for future uses of the launcher. The next thing we're going to look at is the accuracy issue. So our ball is 0.04 meters in diameter, and the goal is 0.2 meters in diameter. So again, we need to take into account that the center of the ball needs to be far enough away from the side of the target wall in order to actually make it in the target. So once you do that, you're going to find that your range is really more 0.16 meters. And then again, we're going to convert that into inches, so that gives us 6.3 inches, and that's the range that the ball can land and still make the target. So over here we can look and see that the mean data is 11.5 inches, which is already outside of our range, which does not bode well for our accuracy. And then if you look through the data, about 3 out of the 21 times that we tried it, the ball landed in that 6.3 range, which means that there's about a 1 in 7 chance of the ball making the target based off our accuracy. So our launcher is not very consistent. Not only is it not making it into the target, but it is, if you look at the numbers, they are not close together really at all. They're very unpredictable. And this is reflected both in our standard deviation, which is pretty high considering we're looking at a lot smaller numbers than we were looking at last time, and then our high z-score. So that's saying that the maximum and minimum points in our data are really far away from our mean. So we have a wide range of data, and again, we're looking at smaller numbers in this case. So like I was just saying, our system certainly lacks consistency. It's not super predictable in either way, but especially in the accuracy. Not only does it not often make the target, but it's not even shooting in a consistent area off the target, so it's not like we could easily recalibrate it. And then here's the 3D model. So our plan was to mount the webcam here just by some sort of adhesive. We were going to try to fit it pretty snugly between these two parts. And our deal was that it would be easier to calibrate if it's pointing the same way as the launcher, and if it turns, the circle here is the rotating base. If it turns on the base with the launcher, then you won't have to recalibrate. But now we're thinking if the target was too high up or was too low, the rotating base would actually block the view of the camera. So maybe we'd want to consider moving that out further. but then we were worried about the wires getting tripped up if we did that. And then also our actual launcher was really hard to replicate, and it required a lot more user strength and reloading. That one would not be safe for kids, and two would just make it hard to keep the powers accurate. And then the other problem was that these there wasn't a real plan on how we would take apart this launcher or reassemble it in order to fit it into the box. So if these parts came out too high and we couldn't put the lid on, there wasn't a plan B. And then also, as far as what we were actually using to launch it, it was another piece of wood that may or may not have fit in the box, but if it didn't, there would be no way to take it apart and put it back together. Thank you.